So I think, let's see, test 1, 2, 3. Yeah, the hanging mics are working. And speakerphone says it's working, so we should be able to hear them. There's the right board here. The only kind of note I would make that I found is a little bit weird about this, I would write even bigger than you think you have to, right? Writing for a room normally on the board, you gotta write bigger than you would on a page, of course. Yeah. For it to come across on the camera, even bigger. So, you know, be bold with your pen strokes. And then let's make sure we just put markers. Well, I do think that's 9:20. It's like there might be a little bit light on the phone.
Private lesson.
I don't know. Yeah, I did do work for my non-honors class yesterday, and that video is up on my YouTube channel. So there's a chance that some people were like, "Oh, I don't have to." I doubt it. I don't think that many people pay attention. It's just Friday.
So should I start then? I'll wait.
9:19, right? Yeah.
I'll wait
Okay.
5
We got a minute. Yeah, we don't need to rush it. Let's see. Grant is here online. Sarah's not here yet. So yeah, probably we'll hold off a few minutes and let some folks come in. Well, maybe while we wait. Just take the video, I'll pan back over here and do the normal title card thing. All right. Good morning, Grant.
Morning.
Uh, 21st, 22nd?
21st.
This mirrored how it should be. Can you guys read, my folks online, can you guys read the board, or I need to mirror that? Anybody? I really can't hear.
The board is good.
Are we getting audio through?
Yeah, the board is good.
I haven't heard a response
good.
yet. Just trying to check to see if we've got incoming sound.
Can you hear me?
Oh, okay, yeah. So we don't hear you yet, but you can hear me okay? Okay, let me try. This other speaker system. Okay, could I just ask you to say something again?
Can you hear me?
Oh, there we go. Okay, so the speakers on the computer will work. I'm going to try to switch it back over to the speakerphone in the classroom. So I'll ask you 2 more times to just say something, whatever you want to say. You can sing, whatever.
Good morning.
Okay, nothing on those. Maybe the separate power thing for the speaker array. Oh, no, speaker array is. The volume on this.
Those things. The circle ones.
Oh. Okay. I don't see a control. There are controls on here, and I've got the volume all the way up, and it's not muted. Can I get one more something, chirp, noise, whatever?
Morning.
Nothing. Okay. All right, then we're just going to have you guys coming out the speakers on the computer for today, because for whatever reason, it doesn't want to play nice. Okay, one more. I'm sorry.
Hi there.
Okay, beautiful. All right, so today Daniel is going to teach us about work. You guys who have done this before know that it takes a great deal of bravery, so let's all just be kind and polite, ask questions when questions are called for, and you know the deal, right? I'm going to pan over here to the other board, go sit my ass down in a chair, and let Daniel take over for the day. All right, buddy, you're up.
Where's the black one?
Oh, I'm sorry, it's on the desk.
Okay. Hi, my name is Daniel, and I'll be doing the work section for today. And work is a physics concept, so I guess we're gonna be talking a little bit about it here because it's math related and it involves calculus. So basically, work. Okay, I'm gonna write bigger. Work is action done on an object that displaces the object. And the unit for work that we're going to use is, there's 2 units, but I think Professor Fossicker wants us to use joules.
Most of the time, yeah.
Yeah, because, well, the units are Newton meters, Newtons times meters, or joules, and they're equivalent, so you can interchange them. They mean the same thing. And an example of work would be like pushing, if I push this desk, actually, I don't know if you guys can see the desk, but if I push the desk 10 feet with a constant force, the way we would find the work on that is work equals force times distance. And what I like to add in the end, and I mean, it'll stay true always too, is cosine of theta. And cosine of theta is used if when the force you're applying is not directly in the direction you're pushing it, then you're supposed to take the cosine of that angle between the axis you're pushing it and the direction the force is going. And if I'm pushing the desk and I'm pushing it perfectly in front of me, then theta should be 0 and cosine of theta is 1. So then we don't even have to worry about cosine of theta. But if I'm pushing the desk and like I'm pushing it down like this, the only work or like force that counts is the force going in the x direction. So that's why we take the cosine of theta. And force is, many of you may know or may not know, force equals mass times acceleration, and acceleration could sometimes be gravity, same thing. F equals mg, that might be more recognizable, I'm not sure. But let's say one example, if I have a box on the floor and there's a force going perfectly across, say a person is pushing it, then if the force is 10 newtons and I push it for 10 meters, work equals force times distance, 10 times 10, that'll be 100 newtons for that. And then, or I don't know if you guys saw that, but it was 10 newtons, 10 meters, and 10 times 10, force times distance. Cosine of theta is 0. And theta is 0. Cosine of 0 will be 1. So it'll be just those. But if the force was like in this direction, let's say, and the person's here pushing it, how a normal person would push it by putting some force down also. Let's say theta equals negative 30 degrees, which is negative pi over 6. It's going to be, and let's just say it's 10 newtons also, and 10 meters, then it's going to be work equals 10 newtons times 10 meters, and this is where the unit Newton meters comes from, times cosine of pi over 6, negative pi over 6. And the cosine of negative pi over 6, if you consult with the unit circle, it's going to be 1/2. And so we're going to have 100 times 1/2. That's going to give us 50 Newton meters. So that means we did 50 Newton meters of work there, or 50 joules of work, either or works. But this is the algebra part, the simple part. I mean, I think the other stuff is not that bad, but this is the much more simple stuff. I'll give you 5 more seconds if you're copying anything down.
While you pause, let me just insert for anybody listening that the problems you'll encounter in the homework, we're generally going to be setting these things up so you don't have to worry about the direction the force is applied. The force will usually be applied directly in the direction that your axis is pointed. So we won't usually have to worry about the trim. But in physics problems, the vast majority of real world problems, that's necessary. And then the one other little comment is that joule is also a measure of energy, right? So work and energy are measured with the same units. So if it feels like there's a connection between the energy you expend to do something and the work required to do something, there is connected to the work energy.
I'll leave this up for now because I still have this big space here. So the next problem I'll go over quickly. Another situation, say you have 2 planets or 2 things in space and don't remember the equation exactly. So if you have, I don't know, the Earth here and the moon here, probably not a good representation, but you want to find how much work is done on like the moon by the Earth. So you take the formula for gravity, which is the gravitational constant, which we don't know, but just bear with me. It's an example here. It's actually pretty easy, this one. And then the mass of the first body times the mass of the second body. Wait. Oh yeah, okay. Force equals, okay, that M1, M2 over R squared, where R is the distance between the two planets. So you have this. What you're going to do is you're going to take the integral. Where am I going to write this? Here. The integral from A to B of G times M1, M2 over R squared, and it's going to be dr. And I mean, this may look complicated, but everything on the bottom, I mean, on the top is a constant. This all moves here. And I'm going to go over here now. So G, M1, M2 over R, no, not over R. M2 times the integral from A to B of 1 over R squared dr. And the integral of 1 over R squared dr, it's going to be, you move the R to the top, it's going to be R to the -2, integral of R to the -2, A to B, which is going to, you're going to add 1, it's going to be R to the -1 over -1, which is going to be -1 over R. And that, and then you're going to evaluate -1 over R. I'm going to put this somewhere better. I don't care about the planets anymore. So it's going to be -1 over R, evaluated from A to B, whatever that A to B is. And then you're just going to multiply it by gravitational constant, and then mass 1, mass 2, and mass of Earth, mass of Moon, or vice versa. Doesn't matter. And that's going to end up being -1 over B minus -1 over A times all that. And I'm not actually going to do a problem with that. Or I mean, I'm not actually going to plug in numbers for this one. I was just showing an example.
So just out of curiosity, this is the work that the Earth does as work does to the moon as what happens? What's the motion?
The motion there is,
Is that like if the, I'm trying to think, so if we're integrating dr, we're thinking about the moon moving along the radial distance to the Earth, right?
yeah, so the work the Earth is doing on the moon.
Like to
It's
keep the moon
moving,
in
because
its
it's
orbit?
constantly pulling it towards it, right?
Okay, yeah, to keep it in its orbit.
Or it's trying to, at least.
Okay.
I think the Earth is actually not doing a good job of pulling the moon.
I was thinking,
But-
right, because if the moon stays in its orbit, then the two R values, the balance for integration should be equal to each other, right? And then what
Which
would
R
we get
values?
if A and B are equal?
If A and B are equal.
I mean, -1 over G.
No, well, actually, I think the moon is actually getting farther from Earth, but it's ever so slightly.
Okay, so
Right.
if A was where the moon is, the distance from the moon to the Earth right now,
Mhm.
and B was the distance from the moon to the Earth
And
sometime later, as the
million
moon
years.
drifts away. Yeah, then this is how we would calculate the work that's done.
Yeah,
So if B is bigger than A, this is gonna be negative.
if B is bigger than A, B being
Yeah, so yeah, as the moon drifts away from the Earth, negative work is done,
yeah,
right? Because the Earth is doing a shitty job, like you're
yeah,
saying.
because the Earth is supposed to be pulling it towards it.
Yeah, that's cool. This is not an example I'm familiar with, but that's very nice.
I actually don't know where I got this example, but I had it written on here.
Oh, it's neat.
Forgot. So, what's next? Another simple example that I'll give I should have done it before lumped together some examples. But okay, I'm gonna erase this. So here, really simple example. If we're lifting a book or I don't know, any object up from the floor, say to a desk. So we'll just draw a little diagram here. This book on the floor, we're lifting it up here. Or we're just lifting it to that height. We're not going to consider the X there. We're just going to consider the Y.
Yeah, we don't have to fight gravity to move it sideways.
Yeah. But anyways, let's say you have to remember work equals the force times the distance. If the book is actually that could be very heavy. Let's just say it's 2 kilograms, and the distance here is 1 meter. 1 meter. Fine. You have to do force times distance times, well, I guess this would be sine of theta because we're on the y-axis. But-
So think of theta as the angle between the force you're applying and the force you're fighting. So
Mhm.
gravity is pointing straight down, the force you're applying is straight up. So the angle between them that would be 0. So the
Yeah.
cosine of theta would be 1. Yeah. So the cos theta goes away.
Mhm. Okay. Oh yeah, because the sine of 0 would be
Yeah, sine of 0 would be 0.
0.
So if
Yeah,
you're
okay, so
straight-
there's cosine, yeah. Okay, but anyways, we have to do, we know the distance, it's 1 meter. We know the weight or the mass, and we have to find out how much force that does. So force is mass times acceleration. In this case, the acceleration is gravity because we're on Earth. So if we do F equals mass 2 times gravity, which we're going to say is 9.8. I actually don't have a calculator, but what is that? That's 19.6, I think.
19.6.
Okay, so force is going to be 19.6. Work equals force times distance times cosine of theta. So it's going to be 19.6 times distance 1 times cosine 0, because we're just considering this. We're not doing this.
Yeah, and then you could consider the horizontal motion there, theta would be 90 degrees or pi over 2.
Yeah.
So the cosine of that would be 0. So you actually do 0 work in moving the book horizontally.
Yeah.
We're only fighting the force of gravity as we lift up.
Mhm.
And maybe work explaining where the 9.8 comes from.
9.8 is the unit, or not the unit, it's the amount of gravity there is on Earth. It's 9.8 meters per second squared, and that's the acceleration. These two are, I just swapped it for G because G is the acceleration on Earth. If we are on Mars, I don't know, maybe we put M. But
I feel a little complicated, but
yeah, but acceleration is the acceleration. So if you were pushing something and it was accelerating, you would use whatever the acceleration is for that, plug it in there to find the force.
yeah, on the surface of the Earth, everything is always accelerating down at
Yeah.
9.8 meters per second squared.
Mhm.
You don't feel it because you're spinning also. Well, you feel that's your weight behind that.
It's not completely necessary, I think, for this class, maybe not yet, to know that 9.8 is the thing, but probably learn it in your physics class, considering if you're taking Calc 2 here, you're probably going to be taking physics at some point.
And there are problems in our homework set where we need to know the gravitational constant.
So the next problem. So I'm gonna erase this now. I'm just gonna hope you memorized it.
Yeah, so we know.
So let's say we have particle is x feet from the. Can the people online read this?
Yeah, it's all good.
Okay.
Thanks.
But a particle is x feet from the origin, and a force of x squared plus 2x acts on it. So we want to know how much force, or how much work is done on it from x equals 1 to x equals 3. Make that better. So how much work is done on it from x equals 1 to x equals 3? So all the problems I did before, I guess, maybe except for the gravity one, they all involve a constant force. And when it involves a constant force, you can just do an algebraic equation, a simple one, because the force is constant. But here, the force is x squared plus 2x. It's not constant. So here what you have to do is you have to use you have to integrate it. So
before we dive in real quick, what direction is that force applying? And because we're moving from x equals 1 to x equals 3.
we're at x equals 1 and we're moving to.
And is that force fighting us? Is that force pulling the particle back towards the
Here, it actually pushes it, I think. I just didn't copy the exact question down word for word. So let's just say it pushes. Pushes. So
Okay, yeah, so that x squared plus 2x is the force being applied to the
Yeah,
particle
yes.
in order to push it.
yes, so that's maybe it wasn't, but we'll just say it is.
Yeah, that makes sense.
Okay, so we recall work is equal to force times distance. And we're gonna assume this force is, you could put cosine of theta, it's gonna be 1,
Yeah.
but we're just gonna assume it's perfect. So work is the force times the distance, and we know what the force is. Oh yeah, okay, understood. Yeah, so work equals so we're gonna take the integral from A to B. This is when it's not constant force, you take the integral of A to B of f of x. And in this case, f of x equals x squared plus 2x.
So that f of x is the force.
Yes.
And the dx at the end of the
Yeah.
integral is the little distance.
Yes.
So for every little distance this particle is pushed, it's being pushed by the force f of x. So you can
Yes.
think about the thing in the integram. F of x has units newtons, dx has units meters.
Mhm.
So the thing we're integrating, there really is a little element of work.
Yes. So yeah, when the force is variable, you're going to do integral from A to B of the force times the little distance, and where the D went is here, A to B. That's where the distance is.
Oh,
So-
your dx is actually the distance. That's the idea. Yeah.
But I was saying like the actual displacement, because before it was FD,
Right.
and D was I don't know, like a big number, not like a DX, like super small.
You can think of all the little dx's as
Mhm.
adding up to that big distance, which is
Yeah.
1 to 3. And the problem is that because the force isn't constant, we can't just multiply that force times the distance there, which would be 2 meters. But we have to multiply the force at each little part along that path by the distance at each little part along that path. So over the interval from 1 to 3, there's a certain force here and a certain force here and a certain force here, and they're all changing. So we multiply each little distance, which is the dx, times each little force, which is f of x.
Yes. So, so f of x is going to be x squared plus 2x. So we're going to have the integral from a to b, where a equals 1, b equals 3. So from 1 to 3 of x squared plus 2x times dx. And we can call that, we separate this, it's going to be the integral of x squared from 1 to 3 plus the integral from 1 to 3 of 2x, and forget dx, and integral of x squared, we'll move over here, is going to be x to the third over 3, 2 plus 1, and pop on the exponent 2 plus 1 on the bottom, evaluated from 1 to 3 plus 2x is going to be, bring out to 2, x squared over 2, 2's will cancel out. So it's just going to be x squared evaluated from 1 to 3. And what is this here? And x to the third over from 3 to 1. It's going to be 3 to the third over 3 minus 1 to the third over 3 plus 3 squared minus 1 squared. And 3 to the third is going to be 27. 27 divided by 3 is going to be 9. So we're going to have 9 minus 1/3, which is going to be what? 9 minus 1/3, 9 times 2, 7. This is going to be 26 thirds, I think. So on this side, we're going to have 26 thirds plus 3 squared minus 1 squared, it's going to be 9 minus 1, 8. If we want to put them over the same thing, we multiply by 3. It's going to be 26 thirds plus 24 thirds. It's going to be what, 50? Yeah, it's going to be 50 thirds Newton meters or joules of work that the force, whatever it is, does on the particle.
I didn't specify units at the start, but if
Oh,
you see
yeah.
a problem without units specified, it is safe to assume everything is in SI units.
Yeah,
The distances and meters, forces are.
that's something I need to work on myself.
It's all right. So this is actually probably good for me to say to everybody too. This is a math class, not a physics class. I'm not here to beat you up over your units and dimensional analysis. It is nice to be mindful of them because tracking your units can let you know when you understand something or made a mistake. If it should come out to Newton meters and you get Newton meters squared or Newtons over meters, then you know you messed up. But if you leave units off on the calculation, will not get points out.
I have a question. Should I save it for the end?
No, go ahead. What's up?
So you specified when you first started this problem that the force acting was pushing versus something else. What else would it be doing, and how would that affect the calculation?
Before I just said act, which didn't specify if it was like, I mean, I guess it didn't specify now that it was pushing in the positive direction. But for this example, we're just assuming it's pushing in the positive direction. If I said it pushes it in the negative direction, then it would be negative work. But
Yeah, I can add in a little picture.
positive direction, and if Professor Fawcett is drawing something on the other board right now. And I think he'll leave the camera open.
Yeah, I got you.
So essentially same calculation, my answer just becomes negative instead?
Yes.
Yeah, and you can think of that as a consequence of the way Daniel's describing work in terms of the cosine of theta there. If the force was pushing the opposite direction of the motion, then the cosine of theta would be pi, or 180 degrees. So kind of think about, I guess we said it's on the x-axis, right? Think about your particle as chilling in here. And the force, imagine there's some wind blowing this way or something, right? Force is pushing us in this direction, and the magnitude of the force at x is x squared plus 2x. So at every different x value between 1 and 3, a different force is pushing this orange particle. It's always pushing it to the right. But like if you plug 1 in here, you get 3, right? So when the particle is right here at x equals 1, it's being pushed with 3 newtons of force. If x is at 2, if the particle is at position 2, then that's 4 plus 4 is 8. So when the particle is right here, it's being pushed with 8 newtons of force in that way. So the particle starts out here at x equals 1, and it gets pushed all the way over here to x equals 3. And as it moves, the wind is blowing harder. It's getting pushed harder and harder, faster and faster, right? Greater and greater acceleration. So what we're doing there when we calculate this work, think about this guy moving from here to here over this little distance dx. If you take that little distance dx, since it's happening right at x, the force there you can assume is constant over this little interval. So the force, so the work that is done to push this particle just from here to here, from x to x plus dx, you can approximate as that little distance dx times the force at that point, which is x squared plus 2x. So the notation that I like to use is to talk about a little bit of work done to push the particle over this little bit of distance. And it would be the force there times the little distance, which is x squared plus 2x, times the little distance there, which is dx. So the little bit of work that's done to go from just here to here by this variable force is the force that's applied over that little distance, which we can assume to be the same over that little distance because it's so short, times the little distance itself. And then this is what we integrate. All right. So that's a good question.
Oh,
Sorry,
thank you.
couldn't resist.
So is everyone done copying? Take that as a yes.
Good to go, race away.
Okay, so the next problem is a more physics-y thing, kind of too. And it's Hooke's law. And Hooke's law is about springs. So I'll draw a quick picture of the spring here. Okay, so Hooke's law. That it says that the extension of a spring, actually extension or compression, of a spring is extension. Yeah, okay. Extension of a compression of a spring is proportional to the force applied. And basically what this means is that the force equals K times X. And here, X equals the difference. It's kind of like a delta X of the natural length of the spring minus the length you have it at, and whether that be compressed or extended. Let's say this spring, the natural length is, I don't know, 10 centimeters. That's 10 centimeters. And we bring this to 15 centimeters. The X is going to be 5 centimeters. But what we want to do is, when we're doing these problems, is if we have centimeters, we want to convert it to meters. So in this situation, if we had 10 and we brought the spring to 15 centimeters, it'd be 0.05, because it'd be 5 centimeters divided by 100 to get to meters. And K is called the spring constant. It's not actually a constant that you know. It's a constant that you're supposed to find out because every spring is unique, and it's going to have like a different like compressibility or like extendability or whatever. So you'll have to do the problem. You'd have to be given the force and the X, or maybe they give you the force and the spring constant and you find the X. But if we have, let's say we have spring, it is 10, the natural length. I'm going to abbreviate that as NL, or actually call it length, and then we're going to put sub n for natural. This is going to be length final, LF. So X equals length natural. I just came up with this myself. This is not like official notation or anything.
I'm picturing LMAC.
Yeah. Minus LF. So natural minus the final. So this can be negative if you compress it, or positive if you extend it. For the sake of the problem, we just do it positive, so it's prettier. But say no, I was thinking about where I'm gonna write stuff. I know. Okay, I'm gonna erase this stuff. I'll give you like 15, 20 more seconds. But X equals the natural length minus the final length, and the force equals to the spring constant times X, which is this. And Hooke's law is the extension or compression of the spring is proportional to the force applied, and that means it's a linear relationship. It's pull it just that little bit more, it's just going to be, it's linear. It's not going to require like way more force to do it if it's further than if it's like smaller.
Yeah, so the further you stretch a spring, the more the spring fights you.
Yeah, there actually is in the Hooke's law. It says as long as it doesn't go past the limit of
There is a
proportionality.
breakdown point.
Yeah, there's like a point, which I guess this purpose we won't talk about, but I mean, maybe if you went from 10 centimeters to like 10 meters, then you would
probably break the spring. Yeah.
you break the spring, or if it doesn't break the spring, you're past that like proportionality point. Like
Yeah.
the spring's gonna start like bending or something.
Exactly. Yep. Yeah. Material.
Yeah.
This way. But as long as you don't abuse the spring, the force that the spring fights you is proportional to the distance you stretch it past its natural length. So X is how far you stretched it or compressed it.
Yeah. So it's like a delta X. So I'm gonna erase this now so I can write the problem nicely.
The
Huh?
final minus initial, right? Not initial minus final.
If you're
Oh.
stretching, yeah, that's what I was saying.
Oh,
If you're
yeah,
stretching
yeah.
and you want the X to be positive, it would be LF minus LF.
Yeah,
Or if
sorry,
you're
it's
compressing,
actually
then it would be the order.
final minus the natural, yeah. Apologies, it's delta X, so it's final minus initial.
You can just think of X as the distance the thing has been stretched
Yeah.
from its natural.
Mhm. Draw the spring, make it a little bit smaller. But say we have a spring. And natural length is 10 centimeters. And force of 40 newtons is required. 40 newtons required to hold at 15 centimeters. And natural position is 10 and force of 40 to hold it at 15. So first step we have to do is to find K. So the force is equal to spring constant times X. And we know the force is 40. So we can plug in 40 for F. We don't know K. X is going to be final minus initial, which is 15 minus 10 centimeters, of course. So it's going to be 40 equals 5K, but we're going to convert to meters.
Always.
Hmm?
Always meters.
Yeah, always meters. I mean, I think that's the
Yeah,
unit
we
for
don't-
for everything.
Anytime, so because we want our answer to come out in joules at the end, we
Yeah.
want to use, the safest way to do that is to use SI meters or SI units all the way through. So right at the start here, where we solve for the spring constant, we want to convert any relevant units into their SI
Okay.
units. So that 5 centimeter displacement, we will write as
As
0.05.
yeah, because Newton meters is joules and Newton centimeters is not joules. So
Would that be like hectojoules?
yeah, something like that. But 5 centimeters is going to be divided by 100. So it's going to be 0.05 K. And K, if I recall, is going to be 800, I think. Yeah. So K is going to be 800. I don't think spring constant actually has any units.
The units are weird. So it's a measure of stiffness and it would
Oh.
be newtons over meters. So for every meter you
Oh, yeah,
stretch,
that
there's
makes
800
sense.
newtons of force required.
Yeah.
You don't need to use units for K if you don't want to. They are. newtons
For
per
curiosity. There you go. But so we have K is equal to 800 newtons. And if you recall, work is equal to, and because the force extends linearly, initially I thought that you would use just force times distance, but thing is, just be it still changes the force that you're like pulling on the spring, so it's still changing. So we do have to do an integral. Work is going to equal the integral from A to B of F of X dx, and F of X we have to come up with, and so we know that it's 800 newtons for every meter. So it's going to be unit wise, it's going to be 800 Newton meters, and we're going to be multiplying it by X meters. So meters is actually going to cancel out here. Then you have 800 newtons, but meters is going to come back when you have the dx, the little thing is measured in meters. So it actually comes back, it'd be like meters squared over meters, so it's just gonna be Newton meters.
So in other words, little f and big F are the same, right? Little f is the
Little
force,
f.
big F from the top of the right column.
Oh, yeah.
The book does this too. I hate it. They use big F when describing Hooke's law and then little f for the force function that you.
Yeah, I thought it was a little confusing, but I got it in the end, but I hope you guys get it.
So the force at distance x from the natural length is 800x.
Oh, I actually never said what the question was, but
You should probably tell them.
yeah. Question is, how much work from 15 centimeters to 18 centimeters? That's the question. How much work from 15 centimeters to 18 centimeters? And remember, the natural length is 10 centimeters. So our lower bound is 15. And it's going to be the final 15 minus 10. Because remember, it's linear, the force. So we have to, we can't do from 15 to 18 or 0.15 to 0.18 wouldn't work.
Yeah, so the bounds are x values.
Yeah.
And x is the distance from the natural length.
Yes, x is just the natural length here.
So
For the
15
spring
centimeters,
problem,
that's
always.
5 centimeters from the natural
Yeah.
length. And 18
Yeah.
is 8 centimeters from the natural.
We want to remember to convert it to meters, so that's going to be 5 centimeters for the first one. So it's going to be 0.05. And the next one, 18 centimeters, 18 minus 10, 8 divided by 100, 0.08, 0.08. And f of x is going to be 800 meters times x. So it's going to be 800 x dx, and take the integral, it'll be x squared over 2, so it's going to really be 400 x squared, right? X squared over, yeah, 400 x squared. It's going to be 400 x squared evaluated from 0.05 0.08, and I think this actually comes out to a clean number. I'm not sure. Let me check. I don't have the answer written down, but 400 times 0.08 squared minus 400 times 0.05 squared. Is that correct? Yeah. Oh, well, not a clean number, but it's a small one. It's going to be, this is going to come out to 1.56 Newton meters or joules. And it's going to be how we find the work for 15 centimeters to 18 centimeters. So what you have to remember for here is the mistake I kept making. Maybe you guys will make it, but is to, I was wondering why this can't be 0.15, this be 0.18. It's because when we're using a spring, it's from the natural length, and the natural length is the 0 position. 0 position is not 0.
One of the running themes in all of these work problems and in all physics problems in general, if you're taking physics, you've seen this, you have to pick a reference frame, right? Somebody hands you a picture of a ball rolling down a hill or a cart being pushed up a ramp. There is no X or Y axis in that picture until you put one there.
Yeah.
So here, what we do is we choose to draw our X axis parallel to the spring, and then we place X equals 0 right at the natural length of the spring, which is 10 centimeters out from the wall. So when you first look at the picture, it's natural to say, oh, I'm going to make the wall X equals 0. But the smart move is to make X equals 0 at the natural length of the spring, because in Hooke's law, F equals Kx, X is not the distance from the wall. It's the distance the spring has been stretched or compressed from its natural length. So if you want to keep all of the algebra simple, then the smart move is to let x equals 0 be the natural length of the spring. And that's why the bounds are the kind of not obvious values that they are.
Yeah. But
It's also why we had to use the 0.05 in our calculation for k.
to recap, you're given to find one, find the k, convert to meters. So we have we're going to get Newton meters in the end, which is joules, not Newton centimeters. 800 is the newtons per meter times dx meters, and then times your little dx piece, which is measured in meters. So it's going to come out to be Newton meters or joules, whatever you want to put. And then you plug it in, the natural final minus natural length, convert to meters. Same thing up here. Solve the integral, evaluate, and then that's the answer there. And then I'll wait another like 20-30 seconds for anyone to copy.
Yeah, and did anybody
I had a quick question.
Yeah.
Sorry, real fast. The 800x, how is that x not the dx?
Because x is the distance in meters you're stretching it from, or stretching, or no, it's the
force, right? So
Yeah,
Hooke's
it's the
law
force.
says that the force needed to hold a spring at a given position is equal to k times x.
I can add a little picture over here to try to diagram Hooke's law a little bit. If we So it's true, in every one of these setups, what we want to be doing is finding a little force and a little distance. Or not necessarily a little force, but a force and a distance. So if I have my spring here and its natural length is 10 centimeters. What Hooke's law says is that the force that's required to, or the force with which the spring is going to pull back. So this is x equals 0, right? Out here, the natural length is where I say this is my x-axis, and right here is the origin. Here is x equals 0. Hooke's law says that if you're going to stretch this spring out by some distance, so here I'll just label this as x, right? So this distance here is x. The force that's pulling back, the spring force, in this case is 800 times x, where x is this distance. All right, I'll just leave it like this. So this. So your force then is this 800x. That's how hard the spring is pulling back when you're at the distance x from the natural length. And then sort of the idea is, if I want to pull this thing from 15 centimeters out to 18 centimeters, at every position x between 15 centimeters and 18 centimeters, the force with which the spring is pulling back is 800 times x. So when I'm out here, the spring is pulling back harder because x is bigger. When I'm back here, the spring is pulling back, but not as hard. So this x, the distance from the natural length, kind of tells you how hard the spring is pulling back. And then the distance, and if I think about going from this x to some little nearby guy, x plus dx. So this distance here is dx. To go from just here to here, to pull the box just a tiny little bit, that would require a little bit of work, which would be the force the spring is pulling back on this little interval times the little distance. Now remember, this force is measured in newtons. And the distance here, dx, is measured in meters. So your little element of work is 800x newtons times dx meters. And then to get work, you integrate that. And we'd integrate from this position to this position. The 15 centimeter position is 5 centimeters past x equals 0. So that would be 5 centimeters or 0.05 meters out to the 18 centimeter position, which is 8 centimeters past the natural length, or 0.08 meters of this thing, dw.
Okay, so this is just a more specific example of force not being a constant.
Exactly. Yeah, the force here is not constant. The force is a linear function of how far you pulled the thing. And anytime your force is non-constant, that's when you'll need the integral. The big idea behind going from the constant force to the non-constant force problems is that if you look at just a tiny little interval of distance on that little interval, because it's dx long, it's so friggin' short, you can pretend like the force is constant on that interval. So at like 13 centimeters, or x equals 0.03, I could assume that from like 0.03 to 0.031, the force is just 800 times 0.03. And then you're going to add up the little bit of work from this tiny interval, a little bit of work from this tiny, a little bit of work from this tiny interval. That's precisely what the integral does, right? The integral is a continuous sum. So we're adding up the little bit of work to go from here to here, from here to here, from here to here, from here to here, from here to here. And each one of those little amounts of work is 800 times the distance at that point, times the little length of the interval dx.
Cool,
Yeah.
sounds good.
All right, well,
Thank you.
oh, let me pan back over.
Okay. So does everyone have this copied? Take it as yes. Spring was in the other direction, the x was just the negative, and would have been the same thing but negative. So there's that. But another problem here. Let's say we have that's right. Say we have building. And we have a rope hanging from it. And let's say the rope is 100 feet long. And I'm gonna tell you that the rope weighs 200 pounds. And so the question here is, I'm gonna write it down. How much work does it take, or I'm just gonna write, how much work to take to bring the rope from where it is all the way to the top of the building? How much work to bring rope to top? And you're given that 100 feet long, weighs 200 pounds. And the way we're going to do this is, as always, from A to B, or not as always, this is the reason the force here is going to be variable, is because as you bring the rope up, it's going to be lighter and lighter because more of it is going to be just sitting on the roof of the building. And it's going to, I mean, it's when you have half of it up, it's going to be half as light. It's going to require half the force. So we're going to have to do an integral here. So from A to B of f of x dx. And in this case, it's the way we're gonna do it is, if you remember in the spring problem, we had the 800 newtons over meter. And so we're gonna have a similar unit here, I guess, except it's imperial units, I think it's called. I should know, but of pound feet or foot pounds. So if we take 200 pounds divided by feet by 100 feet, we're gonna get 2 pounds per foot. And that's similar to how we have the 800 Newton meters. So we have 2 pounds per foot. And we're going to take this 2 pounds per feet. And what we're going to do is we're going to multiply it by the same thing as before, the x, because x, which is in this case, it's in feet and this is the same exact situation that Sarah asked the question about before, but it's because the force is variable and because of how much the rope is hanging off the building. And so here, feet's going to cancel, and then we're going to have 2 pounds, but we're multiplying them by that little bit that we're considering here, this little teeny bit that's super small. That's measured in feet, so feet is going to come back. And I think the correct way to actually write it is foot pounds. I feel like I've heard it pound feet more on TV, but maybe that's wrong, but I think it's foot pounds. It doesn't matter.
Either one, feet times pounds, pounds times feet. Pound feet sounds more fun, doesn't it?
Yeah, because I've heard that on Top Gear stuff. Car show.
Yeah, I love Top.
Yeah. But yeah, foot pounds, pound feet, whatever. So it's going to be 2x. You're right.
The trick to the setup is we're thinking the little bit of rope that Daniel's talking about that is shaded there on the building, we're thinking of that as being X feet down from the top of the building. So the force due to gravity on that little bit of rope is what is it? It's the weight of that little bit of rope, right? So weight is force due to gravity.
Oh, yeah.
The two, and if that little bit of rope had length dx, and the unit weight for the rope is 2 pounds per feet, then the weight of that little bit of rope right there is 2 dx pounds. And then the distance that that little bit of rope needs to come up is x feet. So we assume that that little bit of rope is hanging x feet off the building. Its weight is 2 dx, and its distance it needs to go is x feet. So the little element of work there is 2x dx. The force on its own is just 2 dx, and the distance is x.
So yeah, I was gonna say I hadn't thought about gravity, but it's actually solved because I mean, they gave you 200 pounds, which is the force, which is the mass times the acceleration. And the thing with that is the mass and the weight is like the force you're causing, and that depends on what planet you're on. This is the gravity, but that's already 200 pounds is already calculated the force.
Good.
So there's that, and that's why we skipped that step. And the book going off the table is that's why we have to calculate it there, because we're for 10, I think. So kilograms is actually a measure of stuff, how much stuff something has.
Yeah, it's mass, which is different from weight.
Yeah, so that's why you have to take the kilograms and multiply by the gravity to get the force. But in this case, pounds is force. So A to B of f of x, and we found f of x through finding the weight per unit of measurement, and we were going to multiply it by x because the force is variable and we're calculating for that little bit. And so we're going to have the integral from A to B, not A to B, from 0 to 100. And just to say something here, 0 is here and the 100 is, or the 100 is like here. And it does seem a little bit confusing, but I think the way to think about it is that work is like the amount of like force you're fighting or that you fought total to bring that up.
I'll
So
also say that the nice way to get this to come out is to think of your x-axis as pointing down.
oh yeah, you can do
So
that too.
X equals 0 is at the top of the building and the axis points down.
Yeah, say this is the x-axis, or you can even say it's the y-axis. You just say
You
call
could
it
just change all the x's to y's then.
y-axis, but let's just say the y-axis goes down. This is actually, let's say this is -1 and this is 1.
That's the idea.
So it's kind of like that.
If we're gonna use y, then we would want to change all the variables to y.
Yeah, that's true, but x is not used for everything.
No, physicists don't give a shit, right? You can
Yeah.
just put your reference frame wherever you want, call it whatever you want.
But yeah, so it's gonna be the integral from 0 to 100 of 2x dx. And just remember it's in pound feet, because put it in Newton meters, then you're probably gonna get it wrong, the point taken off, I assume.
Well, it's just that converting from, so the thing here that the weight, 200 pounds being a force, to convert into SI units here would be a little bit tricky. You would need to find a way to convert that 200 pounds
I don't know, I'm saying if
into
you,
slugs, and then slugs into kilograms, and then multiply slugs by gravitational acceleration.
I was saying if you forgot that it was pound feet and you put Newton meters, you'd lose the
Oh, if you
point.
just mislabeled it.
Yeah, but you-
That's an interesting question. I haven't run into that very much in grading. If you were to leave off units, I wouldn't take any points. So if you were to mislabel units, I might take off a half point.
Yeah, but in this case, we're dealing with pounds and feet, so just for to be safe, I would recommend writing on the side there somewhere where you're gonna look.
Yeah, and that notation with units in brackets, that's very nice.
But yeah, 0 to 100 of 2x, bring the 2 out, it's gonna be x squared over 2. The 2's will cancel out, so we're gonna have x squared evaluated from 0 to 100. And if I recall, 100 squared, because 0 squared is 0, is equal to 10,000, I think. 10,000, yeah. So 100 squared is equal to 10,000, that's gonna be pound feet or foot pounds. And this is gonna be the work done for bringing what's it called? The rope up to the building. And a little twist I have to this is, what if you bring half of the rope up the building? Like you just bringing it up 50 feet. So I'll let you guys talk about that first. If there's anything else or questions or whatever.
The textbook does have a bunch of fun variations on it. I would grab one end of the rope away. Oh, what's up, Sarah?
Sorry, just one tiny question.
Okay.
How did we end up still with one of the feet units if they got canceled out earlier? I feel like there's an extra feet unit that I missed somewhere.
Feet, it gets canceled off here, or maybe I might be doing it wrong. This is the way I've been thinking of it, is the feet cancels out here. But actually, no, X, I think I've been doing it wrong there, but I've just been adding it again later.
In one word, the dx is measured in feet.
Yeah, so the dx is measured in feet. And then I was thinking, oh, well, feet comes back in.
Oh, so the DX is feet. So the feet got, yeah, so they're brought back.
That little unit of like measurement. It's like before where it was meters, dx is meters, and it was like Newton meters. Meters canceled out, and then you multiply it by the dx, which is that little bit, which is measured in meters, but in this case it's feet. And so it's like times dx feet. So it's like feet squared over feet. That's how I was thinking of it.
Cool, perfect, thank you.
Yeah, I'll let you go ahead and do it.
Okay, so we'll move now to what if you just bring half of the rope up? I hope I remember how to do this correctly. We can leave that up there. Well, let me try and do it. So we're gonna try and bring only 50 feet of rope up. And so the first thing we're gonna start with is, we know the force is a variable, so we have to do an integral. So from A to B to F to X dx. And so the force, if you remember, is, I should have kept the 200 up there. 200 pounds total. And remember that the force is 2 pounds per feet. X feet, and then dx feet. It's going to cancel out. It's going to be 2 pound-feet, but times the x there. So we're going to have the integral of 2x dx, and the bounds here.
Depends on how we're pulling the thing, right? Are we still pulling from the top and just like yanking it up?
Okay, so it's going to be the, what's it called? The bounds, that's what they're called. It's going to be from 0 to 40. And the reason we're using the same function is because although we're only bringing this section up, we still have the weight of this dragging along. So we still have to account for that because we're bringing this bottom section up here still, and this section is going on top, and it's no longer going to be accounted for when we're doing the calculation. So we'll be sitting on the roof. So it's basically just going to be this to bring this piece up here, and that's if we're only accounting for this. And then if we account for this too, this other piece that we brought up here, we can, that would be a separate integral that we can do. But this is just going to be the same thing. It's going to be x squared back to valued from 0 to 40. And this is ignoring this piece here. This is, it's dragging along, so we're not ignoring it, but we're not considering it in the work calculation. We're considering how much work it takes to bring this up here, which includes that. So it's going to be 40 squared minus 0. 40 squared is what, like 16,000 or 1,600 or something?
Yeah, I think 16,000.
1,600.
Oh, yeah, 40.
Yeah, it's going to be 1,600. Not joules. I made a mistake. But
Well, it's teachable moments when we make mistakes.
yeah, it's gonna be 1,600 pound-feet. How much was it before? The other one, I forgot now. 10,000. Is that correct?
So it looks like what you calculated there, if the rope was 40 feet long, pull the whole thing up, that's what, that would be the work for that. But it makes a really interesting point that the piece hanging off still at the end, we have to lift that up.
I have to do another integral. That's what it is.
I think so.
Yeah, because I have to account for bringing this to here is what I have to account for.
Yeah, so we'll have
So
to add to that.
It's this, it's gonna be this 1,600 pound-feet. I'm gonna erase this, then I'll just write 1,600 in the corner here, so I remember it.
Real fast, I think I missed something. Why are we calculating until 40 and not 50 again?
Because we're calculating the work it takes to, oh shoot, it is 50.
Oh, sorry.
The example I watched on YouTube, and it was to 40. So it's not,
Yeah,
not
it's gonna be
40
50 and then
squared.
25.
So it's gonna be 50, not 500. 50 squared, and then that's gonna be 2,500. That's why I didn't recognize, or no, there. 2,500 foot pounds, pound feet. Sorry,
This is an interesting variation. I hadn't thought of this.
2,500. And so, yeah, now we're gonna do the other integral.
And that one we can do as a constant force, right?
Yes,
No
that's the
part of that is
difference.
coming up. Yeah, that's cool. 'Cause
That's
the
the,
first half of the rope piles on the building, so it's lighter, but the second half of the rope stays
Yeah.
down.
that's the distinction I wanted to make, is because for the first half, we have to take the integral because we have this hanging down, it's additional weight. And so the force is changing. But on this one, it's just, there's nothing else hanging off of it.
Yeah, none of that goes away as we lift. It's like we
It's-
just have an extra ball. hanging
Yeah,
out
it's
from
just
the
like
nice hanging.
bringing, it's like the bringing the box or textbook up the desk
Yeah,
example.
Yep.
So it's just gonna be 2,500 plus force times distance is gonna equal the work total. And force times distance is gonna be, force is what, it's 2 pounds per feet, 50 feet. So it's gonna be 100, what's the unit? Like
Pounds.
pounds
And then that piece of rope,
times distance.
every bit of that thing.
We're moving this bottom half to here. It's not going on top of the building. We're just translating it 50 units up. It's gonna be times 50 equals the work total. Don't forget 2,500.
And if we're being careful with
The
units,
pound
50
feet.
is, yeah, 50 has units of
Yeah.
pounds.
Yeah. No, this is feet.
Oh,
This is
sorry,
it.
feet, yeah.
And then 2,500 plus 100 times 50, 1,500, 1,500 plus 2,500, 4,000.
So 100 times 5.
Yes, 4,000. Because it's gonna be 25, it's like 25 plus 15.
50 times 100 is not 15. It's
Oh.
5,000.
Oh, yeah, that's true. Is it? Yeah, it's 5,000. Oh, that makes more sense, yeah.
7,500
Okay.
pounds altogether.
We do 2,500 plus 5,000, which is gonna give us 7,500 pound feet of work.
Yeah, perfect. I think there's a cool thing here too. In pulling half the rope up, most of the work is done in lifting the lower half of the rope.
Yeah.
Right? We're actually doing a lot more work to lift the lower half of the rope up halfway than we are to pull the first half of the rope up onto the building. That's kind of cool.
The reason that we're also just doing this algebra equation here is because we're bringing this just up here. It's not going over here, so the weight's not being subtracted. So the force is not variable, it's just a constant.
Yeah, it's very nice. It's almost like we have a weight hanging on the end of our first 50 feet of rope. that we
Yeah,
can
exactly.
subtract with us,
Yeah.
which is very, very cool. We can imagine that second 50 feet of rope is all balled up right. I like it. I like it a lot.
But that's it. And I think class is over.
Yeah, that's well timed too.
So let's thank Daniel for the bravery getting up here. This is, I know this cohort has kind of been moving through, and last semester we did everything online. Getting up and doing this at the board, it's a lot harder. It's a lot harder than doing it online. So this is very commendable. It's brave that you wanted to get up here and do this instead of staying at home and doing it through Zoom. So I appreciate that, and I hope everybody else does too. I wanted to pan over here for anybody who wanted the picture in terms of the little lengths and stuff. So when we go to calculate the work for the original rope problem, Sarah asked about the units. So we think about the 100 feet of rope hanging down here, right? This is 100 feet long. and my x-axis is over here pointing down with x equals 0 at the top of the building. The way we get that integrand is by thinking of a little length of that rope at an arbitrary x value between 0 and 100. We find the force on this little bit of rope, and then we multiply it by the distance that little bit needs to go up. So if this is at the arbitrary x value x, and it has length dx, we can calculate the force, which is the weight, which is 2 pounds per feet. That's the unit weight of the rope, times the little length of that rope, which is dx, measured in feet. So this is where we pick up 1 extra unit of feet, because the dx, that little length of rope, is in feet. And we cancel here. And you see that the weight of this little piece of rope is 2 dx pounds. The distance that that little piece of rope needs to go up is x feet. So then the thing that we're going to integrate is that force times that distance, which is 2 dx pounds, that's the force, times the distance, which is x feet. And this is where we pick up our second unit of feet. And then multiplying all of these things, 2 dx feet times x feet is 2x dx foot pounds. And this is what we integrate from 0 all the way to 100 to calculate the work to come up here. And then Daniel's variation over here with the rope coming up halfway, I think that's really cool. That's a lot of fun. I like that one. Thank you for sharing that. The one other little note I wanted to make on the way out here, I was playing around in the back with the Earth and the Moon problem. Because I'm thinking if the Earth did a good job keeping the Moon in its orb, then there should be no work done. And your setup is still 100% correct. So if the distance between these two is r, right, and I don't know what it is, but it's a constant. We assume usually that the Moon isn't drifting.
Yeah.
In reality, it is. But the force there is gm1 m2 over r squared. And if we assume that the distance between the Earth and the Moon does not change, say is we want to call this
A million, 10 to the 6 or something.
yes, like 284,000 miles, I think, but I don't know what exactly it is. I'll just call it r naught. How about that? Then the integral we would do here would be the integral from r naught to r naught of this function. dr. So if the Moon drifts out or comes in, we would end up with a non-zero amount of work. But because most of the time we assume the distance from the Earth to the Moon stays the same, this would come out to 0. And the calculation is correct. This is g m1 m2 times -1 over r. If you want to pretend like the Moon and the Earth can drift apart, we set it up from A to B as Daniel did. And this is from A to B. Plugging in, we get gm1 m2 times, what is that going to be? 1 over A minus, let's see, so -1 over B minus -1 over A. Yeah, 1 over A minus 1 over B. So if the Moon ends up further away than it started, if B is bigger than A, then B being larger, this would be smaller than this, and this work would be positive. So if the Moon drifts away, right, if B is bigger than A, then this is smaller than this. Yeah, then we're doing positive work. And if the Moon comes in, we're doing negative work, right? If the Moon comes in, then the gravitational force due to Earth is working with the direction. And if the Moon goes away, then the Moon is moving away from the pole. So in general, if the Moon...
Wouldn't we try and consider, like, because the Earth is trying to pull towards, why don't we consider that positive? I mean, I guess it'd just be a perspective kind of thing.
So when I lower the pen, I do negative work because gravity's helping me. I'm not pushing against anything here. When I raise the pen, I do positive work. Yeah, so the Earth's gravity, you can think of the Earth as pulling the Moon in. So like when the Moon comes in, that's like lowering the pen. The movement is in the direction of the force.
But isn't the Earth, it is the force. It's like we aren't gravity, so it's like we're fighting against it to be positive, but the Earth is gravity.
the gravitational field from the Earth is pointing in, right? So the force that we're talking about here is
The Earth
pointing like
isn't
this.
fighting any other force.
Yeah, well, I mean, it is, but we can think of it as happening in isolation. So if we think of the moon's effect on the Earth as being negligible, its mass is small enough that we're not really worried about a force pulling this way. The net force between the two, if you want to think of it like that, if you calculate Lagrange points in physics, is in this direction, and it is this amount. So if you're coming with this force, then you're doing negative work, right? Like if I lower the book down off the desk, I do negative work. If I raise the book onto the desk, I do positive work. If the moon is drifting away, if like something's pulling against that force, then we would do positive work. So if the moon and the Earth stay at the same distance, then this work, then the work is 0. And you can also think about that as being a consequence of the cosine theta thing, because the direction this guy is going, right, his velocity vector is orthogonal to the force vector. The angle is 90 degrees. So as long as the moon stays in a perfectly circular orbit, which it doesn't, and the radius, the distance between the Earth and the moon stay the same, then the work done by the Earth on the moon would always be 0. But if the moon drifts out, then B is larger than A, and this is smaller than this, then positive work is done. And if the moon comes in, then A is bigger than B, this is bigger, this is smaller than this, right? This fraction is smaller than this fraction, then negative work is done. So under ideal circumstances, where the moon is hanging out, not changing its distance to the Earth, the work would be 0. But in the real life circumstances where shit's changing, positive work is done, right? Because the moon is actually drifting away. So that was a fun thing. I like that we ended up with a formula for this in terms of the original distance and the later distance. And I thought it was fun to just revisit that. But again, thank you, Daniel. This is really nice. And I'm glad to have our first student teaching up on a board in the last 2 years. That's amazing. I have to go as well. So I will see you guys on Monday of next week, right? And Monday of next week, I think will be Sarah's student teaching. If I remember correctly, she's going to be teaching us about trigonometric integrals. So integrals of products of powers of sines and cosines, like sine cubed times cos to the 4th, products of powers of secant and tangent, stuff like that.
Are we in this room?
Yep, we'll be back here.
Okay.
All right, so that is it for today. Hope you guys have a good one, and I'll see y'all on Monday.